Is that generally the case that I don't know. Terms are redundant? Okay, let's get started. Let me have your attention. Let's get started. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Seminar Series. Today's speaker is Professor Lee Magid, who is a professor in the Department of Chemistry here at UT. Lee completed her BS degree in chemistry at Rice University in 1969 and received her PhD in chemistry here at UT in 73. She joined the faculty of the chemistry department in 73 and became a full professor in 1987. In addition to her duties as a professor of chemistry, she is the liaison for science and technology between Oak Ridge and the Spallation Neutron source. And in particular, she is the acting director for the Joint Institute for Neutron Sciences. Her topic today is the Spallation Neutron source, a powerful tool for materials research. Lee, welcome.
Thank you. Let me start by asking how many of you are not nuclear engineers? Wow, okay. Then I'm going to tell primarily a story which I hope will be of interest to scientists and engineers in the broadest possible sense. You're going to hear a little bit about the SNS itself, the construction project, and the philosophy behind producing the neutron beam. But we'll try to concentrate on the instrumentation and the kind of science that people will be doing at the SNS starting in 2006. So who uses neutrons? Turns out that really across the physical sciences, some biological sciences, and most engineering disciplines, especially material scientists, chemical engineers, mechanical engineers, civil engineers who are interested in structural materials, use neutrons to probe two things: where atoms are and how atoms move. This was the tagline for the Nobel Prize in Physics in 1994, which was awarded to two fathers of neutron scattering. And when we say that we're looking at where atoms are, we say that we're doing elastic scattering, and we'll go into that a little bit later on. When we say we're looking at how atoms move, we're doing inelastic or quasi-elastic neutron scattering. It means that the neutron is scattered with change in energy, and that's interesting in terms of the interaction with the material. The Spallation Neutron source is a DOE Office of Science construction project. Total cost is $1.41 billion. It is a pulsed neutron source, as distinct from the high-flux isotope reactor at ORL, which is a research reactor, continuous beam, poke a hole, beam's always on. So we typically get a band of neutron wavelengths, if you look at this little sketch in the bottom corner, and therefore a band of neutron energies. And when you detect scattered neutrons, you're therefore interested in not only where on the detector they hit after interacting with the sample, but also when. So you use time of flight to give you your information about wavelength and therefore energy. This is the so-called ISIS span. This encapsulates for you from the 1960s to the present, and then projecting out to 2010, 2020, the kinds of materials, the range of materials that we'll be looking at with neutrons. So if you start at the lower left, magnetism was an early topic of neutron scattering studies. Simple materials, very simple materials, even single metals, if you like. Soft materials really got going in the 1980s, looking at all kinds of polymers, colloids, surface active agents, biological samples. And the trend is to more and more complex materials. That is, if you look at proteins embedded in a membrane, you're looking at 2 or 3 different kinds of soft materials. When we say soft, we mean mechanically soft, easily deformed. So, gosh, for the nuclear engineers, this is a no-brainer, right? Pulse neutron sources produce neutron beams by spallation. Interaction with some sort of heavy metal nucleus. Mercury, in the case of SNS, it's a high-power spallation source. Mercury is a liquid, so you have advantages in terms of flowing the mercury, cooling it. Thermal shock is advantageous. Actually, the Europeans are looking to build the next generation spallation source. They would like to be at 2.5 to 5 times the power of SNS in 2012, 2015, let's say. And they're really at the limits of the materials issues because of cavitation, bubble formation in the mercury at such high power levels. So spallation, knocking out of neutrons, boiling off of neutrons from the mercury nuclei. Some of these are extremely energetic. This is a 1 GeV proton beam, so that you have a very broad distribution of neutron energies as a result of spallation, 20 to 30 neutrons per mercury nucleus. You moderate the neutrons, that is, slow them down by a variety of strategies. You can use ambient water, you can use supercritical hydrogen, and actually SNS will have 4 moderators in the high-power target station, 1 of them being ambient water, 3 of them being supercritical hydrogen. And then beam guides, often super mirror guides, to get the neutron beams out to the instruments. Obviously, there's a large amount of biological shielding associated with the production and moderation of neutrons. This is a multi-laboratory project. Oak Ridge's partners are Lawrence Berkeley Lab for the ion source, so where it says front-end building, cesium ion source, which produces H- hydride ions. Los Alamos and Jefferson Lab are responsible for the acceleration of the H-. This acceleration, as I said, is up to 1 GeV. The first 200 big MeV is warm for conventional linear accelerator. The last 80% is superconducting. And this is a playground, really, for accelerator physicists, because a number of modern accelerator projects, not necessarily all for the production of neutron beams, are interested in superconducting LINAC technology. Then the beam goes around a bend into an accumulator ring, and there are so-called stripper foils, graphite or diamond film, which remove 2 electrons per H-, so that you accumulate proton beam that is dumped to the mercury target 60 times a second, 60 hertz. So this is the high-power target station. Its great strengths are fairly short wavelengths, certainly under 10 angstroms. There are plans to build a future target building, which would operate at 10 hertz. Right? So you have a longer time window to collect your scattered neutrons. Therefore, you can detect the less energetic guys, the ones with longer wavelengths. So we would hope that this one would come along by about 2011. This is the Central Lab office complex. The Joint Institute for Neutron Sciences will be co-located here. I'm going to tell you just a little bit later about JINS' Intellectual Center and our housing and conference facility. This building is funded by the state. Will be located just down the road. This is all on Chestnut Ridge. If you're familiar with the laboratory, if you're on Bethel Valley Road heading towards the main entrance of ORNL, there's a sign now. It's a blinking light. It's SNS. It's up to the right. This is the Center for Nanophase Material Sciences. This is what DOE calls a collaborative research center. It's a $64 million building which will have, very importantly for neutron scatterers, a number of complementary techniques: NMR, light scattering, X-ray diffraction, small angle X-ray scattering, some microscopy. It's going to have a nanofabrication facility, the only one in the southeast. people will make proposals. We hope actually a single web-based proposal to come and use the neutron beams at SNS and to use the facilities at CNMS. This facility is going to have a large number of graduate students and postdocs in residence. SNS will have some as well. There will be approximately a dozen research focus areas which are being planned with the national user community presently. Just before we go on, at the bottom, a couple of the characteristics. SNS is going to start operating at 1.4 megawatts. That's the 1 GeV proton beam. With experience, they expect to be able to go to 1.3 GeV, and so be a 2 megawatt facility. ISIS in the UK is the leading source currently, so SNS will be a factor of 10, just in terms of neutron flux delivered to the instruments, a factor of 10 beyond ISIS. And then with a variety of instrument optimization, SNS will in fact be, in many cases, 50 to 100 times the capability of ISIS. The HYPER is, through its readiness review, the beryllium reflector has been changed out. They expect, or they hope to start this month actually. They're going to operate for a few months and then go down and install a cold source, supercritical hydrogen, for a new cold neutron guide hall. So there's exciting things coming for the material sciences community at ORNL. Just some pictures of the progress. This is construction this summer on the front end building where the ion source is housed. This is the pad for the LINAC. All 1,000 feet have been poured, and about 700 feet of the LINAC tunnel have been poured. This goes about 50 feet a week. It's a forum which moves. You reposition it at the beginning of the week, pour. On Friday, you check out, is everything okay? You reposition it for your next pour on Monday. These are the holes for the RF penetrations. It's a fairly complex tunnel. Okay. This is the target. Actually, Saturday before last, 260 concrete trucks provided a pour for the front end of the target station. This is where the beam comes from. This hill in the background is where the accumulator ring is. You can, in fact, see one of the pads for one of the instruments sort of in the back corner. There are sticking up from the floor of the target station 950 reinforcements. There's a cave, or actually a network of caves. There's a lot of karst or limestone on the Chestnut Ridge facility. So there is rebar that goes down to bedrock, 950 of those. And then you can see as they start to build up the superstructure for the target building at the upper left. SNS will be a user facility. That means that we've done a lot of work, primarily over the last 5 years, in engaging the neutron scattering community. There are about 1,000 of us in the U.S. We would like to be about 4,000 strong in 5 to 10 years. That's the size of the community in Western Europe, and we have about the same population. So we've had 40 large and small workshops and conferences, and we have a very large experimental facilities advisory committee for the SNS. There will be support of all kinds, technical, scientific support, scientific collaboration, logistical support, as I told you, places to stay, computing facilities, and so forth. Access to most of the instruments will be by a peer-reviewed proposal system. We'll use what's called a PAC, a Proposal Advisory Council, actually probably several of them. And we hope to have up to 2,000 users per year when SNS is fully operational. The bullet about flexible instrument strategy is foreshadowing the fact that some instruments will be built by teams who come in with their own funding from outside the core SNS project and say, we'd like to do a specialized instrument and we'd like to have the majority of the beam time on that instrument. Okay, just to give you an idea of the things that the Joint Institute of Science is doing, in our startup here, we're focusing on building the community. So first week in October, we had a workshop with 160 participants. About half of them are from the community for the engineering materials diffractometer, which is called Vulcan, after the Roman god of metalworking or something, I guess. We're going to do neutrons and biology in the spring. Biology is an interesting area in terms of the diversity of people who look at biological materials, and so we have a challenge there. We have actually permission already to use the title Jins Professor. All of the joint institutes between UT and ORNL are asking the provost for funding for a joint institutes professorship program. We don't have the funding yet, but we have the permission to use the title. Actually, one of the first Jins professors will be my new colleague in chemistry, John Larice, who studies materials adsorbed on model catalysts. There's a UT Neutron Sciences Consortium, which includes Professor Townsend from this department, and we are planning to roll out a series of graduate courses, interdisciplinary, across all of the sciences that use neutron beams. We hope to do the first one actually in the spring semester. These will be special topics courses initially. We are also looking to nucleate small groups. For example, neutron spectroscopy, the neutron analog of infrared spectroscopy, is very interesting to a number of people. This is an inelastic technique, and so we are planning a small workshop in that area. We still haven't heard, although the Energy and Water Appropriations Bill has been signed, whether we're going to get the first-year funding for a graduate student fellowship program, but we're still reasonably hopeful. There are 5 instruments. There's room for 26 instruments on the high power target station. There are 5 instruments for neutron scattering which are funded within the SNS construction project. Those are the high resolution backscattering spectrometer, 2 reflectometers for studying magnetic materials and studying liquids, an extended Q range small angle instrument, and then the 5th one funded within the project is the 3rd generation powder diffractometer. Where it says IDT, that means Instrument Development Team. There are 2 of those instruments, both for inelastic scattering, which have been funded separately by the Department of Energy. And this is this example of a group that comes together and gets funding for its instrument outside of the core SNS project. We expect that the engineering materials diffractometer, that's Vulcan, will be the 8th instrument funded. The Canadians have what's called a Fund for Innovation. It's likely that they'll provide half, and we're reasonably certain that we know who will provide the other half. Similarly, for disordered materials and for the high-pressure diffractometer. Disordered materials will be largely chemistry and physics, and it's reasonably likely that the National Science Foundation will be interested in that one. High-pressure diffractometer, earth scientists are really interested in this. They're interested in minerals at very high pressures, issues about instabilities in fracture zones, predicting earthquakes, for example. The Carnegie Institution of Washington is putting a great deal of money into novel, very high-pressure cells to use on this diffractometer. And again, we're hopeful that the National Science Foundation Earth Sciences Division will be interested in that one. Spin echo is a quasi-elastic neutron scattering technique. ULIC, which is a European neutron scattering facility in Germany, has signed a letter of intent saying that they're going to build that instrument. And fundamental neutron physics is an initiative of the ORNL Physics Division with a number of universities. That group had a workshop this past September, and they have a proposal due to DOE the end of December, and that one we're fairly optimistic also will be funded. So this is the layout. Proton beam comes in here. As I said, there are 4 moderators, the so-called upstream moderators and the downstream moderators. The downstream moderators are both supercritical hydrogen So those are for longer wavelength neutrons. The lower upstream monitor is ambient water, and the higher upstream monitor is the third supercritical hydrogen moderator. These pulses are 800 nanoseconds in width. They come 60 times a second, and they're 800 nanoseconds. The rest of the time, you are collecting information about the scattered neutrons. And so these instruments view various moderators depending on their characteristics. For example, this chopper spectrometer is interested in fairly large energy transfers. So it's interested in fairly energetic neutrons. It views the ambient water moderator. This just shows you the 7 instruments that already have their funding, but believe me, the real estate is fairly well staked out for the others. Why are material scientists interested in neutrons? We are interested in them primarily for 3 reasons, aside from the fact that the wavelength is in the right range. Contrast variation. Scattering cross-sections do not vary, as is the case for X-rays, which are scattered by electrons, according to atomic number. So you have very nice differences in scattering power. If you look, for example, on the right-hand half, the neutron side where it says 1 and 2, that's just H and deuterium. They have very different scattering lengths. Square that, you can say they have very different scattering cross-sections. There are other isotopic examples, iron, for example, nickel, cobalt, when you get over to the heavier atoms. So there's great sensitivity to light atoms. This is incredibly powerful with polymers, with lipids, with biological materials, proteins, nucleic acids. Neutrons are penetrating. X-rays are much less penetrating. So if you want to look at large objects, if you want to know why a section of a high-speed rail line fails, and you've got a big enough frame, big enough sample area to handle it on an engineering materials diffractometer, you can load it and look at stress, texture, what's happened at the grain boundaries of the material. Can't do that with X-rays. Very nicely penetrating. And the neutrons have spin, right? They have a magnetic moment. So you can look at magnetic structure, arrangement of magnetic spins in a material, as well as atomic structure. So courtesy of Roger Pinn from the Neutron Scattering Center at Los Alamos, neutrons are scattered by nuclei, as we've already said. Neutron man comes in, and we have Bragg's law, right? We have diffraction, which corresponds to the interatomic spacing. Now, we're working in reciprocal space, right? We're working in momentum transfer space. So think roughly that the larger the distance you want to be able to probe, the smaller your Q value has to be. So you have to go to very small scattering angles, small Qs, which means long wavelengths, low angles, in order to detect the signal from large-scale structures. The other kind of neutron scattering is quasi-elastic or inelastic. So our neutron scientist is illustrating with a bunt. And now the energy of the incident and the scattered neutron are different. And you can look at all kinds of energy transfers. You can look at vibrations. You can look at phonons. You can look at magnons. You can look at large-scale motions in polymeric materials. You can look at rotations of groups of atoms adsorbed on a catalyst surface. So let's just look at a couple of maps. This is elastic scattering science. Across the x-axis, we have Q. And so at the left-hand side, we're looking at large-scale structures, low Q. We need different Q resolution. We need to be able to resolve at the level of 1% or even less, perhaps, if we want high-resolution structures. We also might want high intensity. We might have weakly scattering samples and be able to get away with moderate resolution. So you have your Q resolution along the vertical axis. This just puts some of the instruments. You see the liquid reflectometers and the magnetism reflectometer. Magnetism reflectometer is a misnomer. It just means that the sample is mounted vertically. And so people who do samples that don't flow, they don't have to be magnetic. You can use that very nicely. You see the engineering diffractometer, Vulcan. PowGen 3 is the powder diffractometer. Then we have various other diffractometers. And then at the upper right, we have the various SANS instruments, and you can see that they cover quite a range of Q, and by paying attention to the configuration, quite a range of Q resolution. And then if you look at the inelastic map, this just shows you the coverage. The first two entries are the same Fermi-Chopper spectrometer, and then as you go down, you're looking at lower energy transfer. So it matters what kinds of motions you're looking at. If you're looking at rotations of groups on catalysts, those are pretty low energy. If you're looking at molecular vibrations, bond vibrations, those are higher. And you can see that the map is reasonably well covered, but there is certainly room for additional possibilities. In particular, if you look at the sort of the Kentucky blue, the backscattering spectrometer, one need that the community has identified is to stretch that range of coverage. They would really like a survey instrument. What they're saying is it's great if you know exactly where you are in Q space already or where you are in energy transfer, but you don't always know that with a new material. You don't know what's going to be interesting. And so you want an instrument where you can come in and do a survey and then focus in. You also sometimes want to add banks of detectors so you can do elastic scattering on the same instrument where you're doing inelastic scattering so that you get a kind of a twofer. Okay, what we're going to do for the rest of the talk is go through some of the instruments and look at some examples of science that people would do with these. And first up is the small angle scattering instrument. This is within the project. You're going to see a lot of instruments that look sort of generic, sort of along the lines of, well, we've got some choppers in there to define the bandwidth. We're not going to look at every wavelength that we're given. We're going to define that a little bit because we know what range of Q we want in different settings. The power of this instrument compared to SANS at a reactor source is the range of Q that you can do in one instrument setting. That's incredibly important if you have a complex material with multiple length scales. You know, from things on the order of a few interatomic spacing up to very large objects where you'd like a medium or low resolution picture of the overall size and shape. When we say performance 3 to 5 times that of D22, D22 is currently the best small angle neutron scattering instrument in the world. It's at the Institut Langevin in Grenoble, France. And don't worry, I'll pick it up later. Actually, the HIFER with its cold source installation will have 2 new small angle instruments as well. So that I think what the community will do, you notice that this one says moderate resolution, we'll pick our instrument according to what our problem is. If we have a weak scatterer, we're likely to need the very intense beams of this SANS instrument, and so we'll be at SNS. If we have strong scatterers and we're interested in very high resolution, very good resolution in delta Q, we'll be over at the HIFER. Despite the simulation here, what I'm talking about when I say good resolution is the fact that these dips, where you have nicely monodispersed spheres, for example, these dips are critically dependent on resolution, because if you have a considerable spread because of pixel size or convolution of wavelength spread on your detector, these maxima and minima get smeared out. And these are related, very importantly, to characteristic dimension in the sample. So that's the SANS. And because I study micelles, now you get a brief detour into micelles. What are micelles? These are self-assembled objects formed from surface active agents. These are detergents. So you use these every day, whether you use bar soap or liquid soap or laundry detergent, you are using, or mouthwash, you could go on and on and on. You are using molecules of this sort. They are very simple. They're a nice long alkyl tail, a nice chain of carbons, some kind of a charged or at least polar head group that's soluble in water, and some kind of counterion. We study surfactants which make very extended micellar objects. Why? Because these objects in solution make the solutions viscoelastic. Solutions at very low concentration of added surfactant are both viscous, so it's like honey compared to water, but at the same time they're elastic. They have a characteristic that's like a rubber band. If you entrap bubbles in these solutions and swirl the solutions, the bubbles go one way, you stop swirling, they come back the other way. So it's like stretching a rubber band, and it comes back to its original shape. So we play this very simple game with these molecules. This is a cross-section of the micelle with its counterions, its negatively charged ions. These are the head groups, the little open circles. And our counterions have a variety of organic structures which we choose so that we can tune the viscoelasticity. So why do we care about these? Well, on the one hand, they're great models for other worm-like molecules like nucleic acids, like actin, which is the cellular structure in the cytoplasm, gives interesting viscosity properties to the cytoplasm of a cell. There are a variety of commercial polyelectrolytes. These are used in all kinds of applications, things like absorbent diapers. Okay, the modern disposable diaper has a lot to do with polyelectrolytes. We are interested in how you tune these worm-like micellar structures and how they overlap as you increase their concentration in primarily aqueous solution. We're also interested in testing theoretical models for how flexible they are and whether we can tune that by changing the structure of the monomers of which they're made. So we need some kind of model because we're operating in reciprocal space, in Q space, for the scattered intensity. Here's our polymer with its characteristic dimensions. It has an overall length, if you stretch out this piece of spaghetti. It has a persistence length, a length over which it's rigid. It has a cross-sectional radius, which changes with the molecular structure of the monomer. And so we apply this scattering theory to how we expect the intensity to be affected by these parameters. Here's the overall contour length, here's the persistence length, here's the cross-sectional radius. This is not a scattering theory that we developed. It was developed primarily from Monte Carlo simulations, which produce analytical solutions for the scattering. And so here are two different surfactants, cetylpyridinium with a bromide counterion and cetylpyridinium with a little bit of aromatic or salicylate counterion. The salicylate increases the micellar rigidity. They're harder to bend. The bending modulus goes up. And in fact, you can see this as a function of concentration for the two cases. This is salicylate, this is the bromide. These are what are called bending rod plots. This region is sensitive to the cross-sectional radius. This region is sensitive to the persistence length, the scale on which the micelle is rigid, and this height of the peak over the plateau is sensitive to how long the micelle is, to how many persistence lengths there are per individual micelle. This is something that we could not do 7 or 8 years ago. The theory has only become available rather recently. Now, I want to show you another kind of aggregating material where the aggregates are much larger. This is a complex which is important in cell signaling. This is actually important in molecular motion or molecular machines which occur in biological systems. We have protein A and protein B. This is a regulatory protein which tells this protein act on your substrate or don't. When these two guys bind, they change shape. When they bind an inhibitor, an analog of the substrate whose reaction this protein, which happens to be an enzyme, catalyzes, there's another shape change. So what do? You label. You say, okay, E. coli, I'm going to feed you amino acids. Make me a deuterated protein. Make me a deuterated protein, and I'm going to look stepwise at H protein, D protein, H inhibitor, D inhibitor, and I'm going to look at how the scattered intensity changes with these different deuteration patterns. This is the work of Jill Trujillo, who directs the biology division at Los Alamos. She is also Associate Director of the Center for Structural and Molecular Biology at ORNL. They're building one of the SANS instruments at the HIFER. You combine this low-resolution work, this work which tells you about the shapes of these complexes, with the high-resolution information at the bottom left. The high-resolution information comes from X-rays. It also comes in part from NMR spectroscopy. So this is meant to highlight the fact that complementary techniques are extremely important. You don't get it all by neutrons, but you get key pieces of what you need. This is another example of HD substitution. If you're interested in what an individual polymer strand is doing in the pure polymer, in the polymer melt in this case, the elegant way to do this is to have mostly deuterated polymer, that's the black, and a little bit of H polymer, that's the red. Why? There's this nasty little thing called incoherent scattering. Scattering which comes from the isotopes, which does not depend on structure. It's isotropic. It's everywhere in space, and it adds a background. So you want to minimize that. H is a big incoherent scatterer. D is not. And this was a study looking at actually blends of two polymers and what happens to those blends when they phase separate. This is something that's used technologically to control polymer processing and to control overall polymer properties. The message of the data on the right is that an idea that's about 40 years old, that the polymer chains change size near a phase separation point, turns out not to be true. The polymer chains, which are the blue diamonds, in fact, are size variant. This is something that we call near-surface sands, which a group of us at UT, ORNL, and Los Alamos developed in the early 90s, where we bring a neutron beam in parallel to the long axis of our flowing spaghetti. We want to know on a molecular level why these viscoelastics, surfactant solutions, are drag reducers. It turns out the reason they're drag reducers is that they undergo a flow-induced phase transformation. They go from being micellar solutions to being liquid crystals close to the surface. And the pattern that you see at the upper left and then expanded at the lower left is actually the diffraction spots from this nice hexagonal liquid crystal, which is formed parallel to the flow axis. We do this in a poisé or pancake cell. This is the high-resolution backscattering instrument. This will be used to look at among other things, it's something I already described to you, which was molecules sitting down on surfaces and how the molecules move. In the long run, you can, in fact, look at this to study chemical reactions. You can study different molecules absorbed on catalyst surfaces and look at what happens to them in different stages, not snapshots of reactions as they actually occur yet, but you can do model systems where you can get a good idea of what's going on. This is another kind of work that will be done on the high-resolution backscattering instrument. This work actually comes from NIST, which is a reactor source. looking at the folding and unfolding of proteins. And what you see in the two figures in the middle on top and on the right is the spectrum. In particular, this is as a function of energy transfer. And so what you're looking at on the right-hand side is line broadening of the elastic peak. That is, the information, the energy transfer is sort of underneath there, and you can make a model for the magnitude of the energy transfer going on with the scattered neutrons and get information about the time scale, the dynamics of this folding and unfolding. This is a spin echo instrument at ULIC. NIST has the analogous spin echo instrument now, and something like this will be built at the SNS. Actually, this is an old slide. The instrument at NIST is through commissioning and is accepting users. There's a so-called intermediate scattering function on the right. This is used to look at polymer dynamics, those entangled spaghetti-like polymers, and how their diffusion is restricted. Their diffusion both along the long axis and their diffusion or flexing in between contact points. We're starting to do the same thing with our micellar systems. The reflectometers, these are used to study structure perpendicular to the surface of the material. So let's say that we have a polymer sandwich. We have polymer A, polymer B, polymer A, polymer B. And we'd like to know about the structure. We'd like to know the thickness of the layers, but maybe we'd also like to know how sharp the layers are. That is, have the individual polymer molecules interpenetrated. You do that with reflectivity. This is polystyrene and polymethyl methacrylate. You see the reflectivity trace and the real space is the inset, the real space model of what the structure is. Those would be perfect square wells if there was no interpenetration. This is the work of Tom Russell. He was at IBM Almaden when the work was done, but he's now in the Polymer Science Department at UMass. This is the powder diffractometer. I put it in here to give you a sense of the number of detector elements. Some of the SNS instruments are well above $10 million, primarily because of the very massive banks of detectors. If you had all the money in the world, you would cover the whole sphere. You wouldn't waste a single scattered neutron. And so this shows you fairly ambitious detector coverage. And the next view graph shows you what you can hope to do with this PowGen 3, this next generation instrument. The message here, if you focus just to the right of the midpoint, where there are two minor peaks, if you compare what's possible at ISIS to what will be possible at the SNS, the idea here is that you could look at very minor components in an alloy, let's say. So you had a small impurity and you wanted to know what the impact on structure was. This is the cell, this very high-pressure cell for the high-pressure diffractometer, which is not yet funded, but we expect will be funded. This is Vulcan. The exciting thing about Vulcan, this engineering diffractometer, is how you'll be able to come down in size. You'll be able to look at much smaller samples, so therefore much smaller grains in a large material. It's expected that DOE, EERE, that's Energy Efficiency and Renewable Energy part of DOE, will invest considerable money in specialized sample environments, large load frames, other sorts of large-scale sample manipulation. So you see where it says ancillary equipment will be an integrated part of the instrument. Plan to leverage some resources. This is the multi-chopper spectrometer. This is good for low energy transfer. Some of the work that I described that is done on the backscattering spectrometer can also be done on that one, just a little bit more energetic than the backscattering. This guy now goes to considerably higher energy transfer, spin dynamics in high temperature superconductors, model magnetic systems, excitations in quantum fluids, the difference between helium-3 and helium-4, very interesting fluid. colossal magnetoresistance materials, which are so important in magnetic storage media. Let's say that you want to put a lot of cable under the ocean. You want great bandwidth to carry long-distance phone calls. You'd like your material to have no change in volume with temperature. Most materials expand when you heat them. They have positive thermal expansion. So it'd be nice to have a material that has negative thermal expansion. This is the work of, two years ago, Lucent was going great guns. This was a great example. It still is a great example. Colin Broholm in the physics department at Johns Hopkins works on a particular oxide which has negative thermal expansion. What this is a material which has zirconium surrounded by oxygen and tungsten surrounded by oxygen. Octahedra and tetrahedra. The tetrahedra hangs free. Their motions in the solid material shows the density of states. The motions in the solid material are the reason this material shrinks when you heat it. So this is an example of looking on the atomic level at what causes this rather useful material's property. An example of an antiferromagnetic material. If you want to understand high-temperature TC materials, if you want to understand ferromagnetic materials where the spins are aligned, you also want to understand the anti-ferromagnetic. And so this is a combination of inelastic and elastic neutron scattering information. So you can look at phonons, vibrations, or magnons with inelastic scattering. You can do conventional diffraction to get the location of all the atoms. That's the upper right. And then the lower right, copper has a magnetic moment. So if you polarize your neutron beam, you could do polarized neutron diffraction and get just the structure of the magnetic component of the sample. And then finally, single crystal diffractometry. This shows the instrument that would be primarily for small molecules, but there is also an interest in doing an instrument for very large unit cells, large molecules, biological molecules. Why? Chris Diowitz in the biochemistry, cellular and molecular biology department here at UT has experience with drug companies that design HIV inhibitors. And the idea here is that you want to know exactly where the molecule that inhibits this protease is located in the active site. So you want atom by atom, in particular hydrogen by hydrogen, the distances, so that you can design a better inhibitor, a better drug. If you use X-rays, no matter what anybody tells you about very high-resolution X-ray crystallography, sub-angstrom resolution, you are still inferring where the protons are. And some of the protons, some of the H's are disordered. And so you intrinsically don't get the precise electron density maps which allow you to get information about the H's. You get that with neutron protein crystallography. And so you can do better drug design. You can look at the location of water molecules. You can look at proteins in situ in membranes which aren't easily crystallized. There aren't many membrane protein structures around. Let's see, I think that should be the end. Yes, that should be the end. So I tried to tell you a little bit about the SNS facility itself and then a little bit about the different kinds of science, the different kinds of instrumentation that will be available. Be happy to answer questions.
Okay. We have questions?
Okay.
Magid?
Are you having any real challenges in the design and construction other than the harsh?
Yes. There are problems with the stainless steel, the vessel for the mercury, the very high power proton beam. There are problems with pitting of the surface, and the project is going through various studies and tests with different surface treatment of the stainless steel. It's improving. I think they're using coupons of the material at a test facility in Los Alamos.
I was going to ask you, where are you
It's in,
getting this take place?
Yeah, they're doing,
Plants?
they're using plants. That's getting better, but that isn't solved. And the European Spallation source, obviously, at 5 megawatts, is extremely interested in the outcome of that. There's some other things, but that's the highest profile concern at the moment.
I wanted to ask you just to learn something here. Historically, protons have always been accelerated in circular accelerators. There was CERN, and then our accelerator came. Electrons were accelerated linearly, slack. Now here, I guess superconductivity changed this picture. Because here you have
Actually, the possibility of using a rapid cycling synchrotron was studied very carefully and discarded in favor of the LINAC plus accumulator ring before the decision was made to go from normal conducting to superconducting.
And as a follow-up, when during the construction of the superconducting supercollider, there was the design group was in Berkeley, and they wanted to get an idea what the reliability of this accelerator would be. And so they went to the operations research department there. And there was a major debate. The operations research people said, "You're kidding yourself if you think that you can get the projected reliability." I don't know what the number was. And the physicists said, "Well, we don't believe what you're doing." Now the experiment was never done because the funding was cut. My question here is, where do these numbers come from for the reliability?
I think there is some experience actually in Europe. Jean-Louis Leclerc, who is heading up the accelerator project for the ESS, built the ESRF, the third generation light source in Grenoble. And my impression, I don't know the details of his track record on normal conducting versus superconducting and issues of reliability, but my impression is he's the best in the world, and it's likely that there's European project experience that he's been involved in, which SNS
How many magnets are there?
is happening. Oh gosh, I don't know. A lot. As you can imagine.
Are the instrument systems developed by different research groups? Various institutes?
The instrument scientists, Argonne National Lab has the lead on the instruments. Most of the instrument scientists are stationed at Argonne, and they have come actually from all over the world. So in some cases, they bring design experience from ISIS. In some cases, design experience from IPNS, which is at Argonne, the Intense Pulse Neutron Source. So that's a much lower power source. But in terms of strategies for designing instruments, it's very useful because these guys are constantly thinking about how to optimize instrumentation, focusing optics, for example, to make the best possible use of the neutrons they do have. So you have a kind of a small but rather dynamic world community, which has been in this business for a number of years.
Okay, one final question. Mo?
I'm just curious, some of the data, for example, if you're looking at these molecules and things, are you looking at them in static images, or are you looking at it over a function of time, like dynamic, like growth of crystals or growth of molecules or changes?
Most of what I showed you is a time average snapshot. But, for example, we are able, on a current source like Kuiper, when we do the so-called near-surface sand, we're able to turn the flow off and follow how the spaghetti relaxes and how this shear-induced liquid crystal phase goes away. We can do that with resolution now of order half a minute, or maybe if we're lucky, we have a really strong scatter of 10 seconds. You take that down by a factor of 100 or 1,000 because of improvements in sources. You open up all kinds of new science because there's now time windows that you couldn't access before. Yeah, so there's lots that you can do in situ studies.
Okay. We have several visitors today who may not know about the party that we have after each one of these seminars. And so you're all invited downstairs on the second floor, room 219. There are refreshments. But before we adjourn, for those refreshments, let's express our appreciation to Lee. Thank you, ma'am.
I didn't even think so.
Wow. Well, you've been on the step. So we do want you to go downstairs.
Oh, sure. Actually, I recognize several of the students, Bo and several of the engineering council.
Right.
Special topics.
Right, I remember you said
I said it.
Yeah.
I was at a meeting yesterday in San Diego at Mr. Scott and some data from Ryan Ellis, Grenoble, France.
Okay.
And they showed simulations of the dynamic results they got from scouting rotational translational, and then they also had the DNA molecule where they showed where the water is in the DNA. And they got all that at yellow.
Right. There was a guy at the International Conference on Neutron Scattering in Munich in